Okay, so now we want to translate the first quadrant here. You can see I kept my first quadrant from the previous video, and now we're going to add to that the second, third, and fourth quadrants, okay? The circle might be a little lopsided. I drew it in quarters, but not too bad. So if I take this first quadrant and I rotate it or translate it over to the other three quadrants, you'll see that there's going to be a pattern in the points. In fact, the points are just going to translate themselves over, and we're just going to be changing sign based upon whether the x is positive, negative, or the y is positive or negative. Okay, so it actually isn't too much work to do this. We'll start with essentially the equivalent to the 45-degree angle, and then we'll do the 30 and the 60. And then we'll bring it down to the fourth quadrant and do the same. And the fourth quadrant. Okay, so those are our four quadrants. And what's interesting is that before I really get into the points, I should go through what the angles are in each quadrant. And maybe I'll start with the axes, right? So we have an angle of 0, then pi over 2. If you continue going around, we know that 180 degrees is pi. So over here, we have an s equals just pi on the left, on the negative x-axis. And on the negative y-axis, we have s equal to, remember it's 1/2. 2/2 is pi. This would be 3/2. So this would be 3 pi over 2. Okay? And you can think of it, every 90 degrees is another multiple of 1/2. Okay? So think of it as you got 0, you have pi over 2. These are the s values. 0, pi over 2. Oh, I shouldn't do it that way. If they were in degrees, it'd be 0, 90, 180, 270, and 360. If you just think of them as another pi over 2, so this starts out as 0 over 2, this is 1 over 2, 2 over 2, 3 over 2, and 4 over 2, right? Just increasing by an extra 1/2. And then of course you tack the pi onto each of these. And so you have 0 over 2 pi is 0. So 0 degrees is 0 radians. 90 degrees is 1/2 pi, or pi over 2. That's where that comes from. 180 is 2/2 pi. Well, 2/2 is just 1, right? So it's just pi. 270 is 3/2 pi, or we call it 3 pi over 2. And then 360 is 4/2, right? It's 1, 2, 3, 4/2, and 4/2 reduces to 2, so that's 2 pi. Okay? So everything you can build them up as fractions and then reduce. Sometimes it's kind of nice if you don't remember, if you just don't have them memorized, you can remember that 270, or you can determine that 270 down here is 1, 2, 3 pi over 2, right? It's the third half of a pi, or it's 1.5 pi around. All these fractions are just going to be portions of 2 pi, okay? In the top half, it's going to be just portions of a single pi. So that can help you to remember those values, okay? So over here, okay, so that gives us, and then over here, we also have an s value of 2 pi. So actually 0 and 2 pi end up being the same. They're, coterminal angles, I suppose. Okay. So we can also do the same thing with all the other angles. Let's look at the 45s for a moment, right? So 45 degrees is 1/4 pi, right? Pi over 4. It's 1/4 of a pi. 90 degrees is 2 of them, right? So if I were to increase by 45, you get 45, 90, 135, 180, 225, and then 270, and then 315, and then 360. These are your 45s going down, your multiples of 45, okay? So if I add or increase by 1/4 of a pi every time and reduce, it should work out. So 90 is 2/4, 135 is 3/4, 4/4, 5/4, 6/4, 7/4, and 8/4. And of course, if I reduce all those and throw a pi on them, right, throw a pi on each one, then this is, of course, pi over 4. 2/4 is 1/2, right? So pi over 2. So it works out, right? 90 degrees, pi over 2 again. Just using the 45s instead of the 90s. 135, this is 3 pi over 4. That's the one I'm looking for in the second quadrant here. So S equals 3 pi over 4. Then I have 4 over 4 is just 1. 5 over 4 is 5 pi over 4. That's going to be in my third quadrant. 5 pi over 4 is right there. Then 270 is, well, 6/4 is really 3/2, so that's 3 pi over 2, and we already had that one. 315, that's over in the fourth quadrant, is 7 pi over 4. That one didn't reduce. Oops. I should say S equals 7 pi over 4. And then the 360, of course, 8 over 4 is your 2 pi, which we already had. Okay? So again, you can repeat that pattern all the way around and get your fractions. I always think of it this way: if I'm looking at a circle, or I can picture the circle or even draw it out, and think of my 45s as pi over 4, 2 pi over 4, 3 pi over 4, and if I'm looking for the 45-degree angles, they're the ones that don't reduce. So 3 pi over 4, 5 pi over 4, and 7 pi, right? 1, 2, 3, 4, 5, 6, 7, that doesn't reduce, and then 8, all right? So I always think of those patterns in the fractions. So the denominators on those 45s are all 4s, and the numerators are increasing by an odd number, right? 1, 3, 5, 7. Okay, then we can do the same sort of thing with the 60s and the 30s. I won't go through and write out all the details, since you've seen it a couple times now, but I'll just kind of point and go around. So if I'm looking at the 30-degree angles, that's pi over 6, right? Well, let me think, how do I want to do that? Yeah, pi over 6 is 30 degrees. Then 60 degrees is another pi over 6. So every 30 going around is going to be increasing a pi over 6. So I got 1 pi over 6, doesn't reduce. 2 pi over 6. 2 over 6 reduces to 1/3, right? 3 pi over 6 is 1/2. I'll ignore the pi's, I'll just say 3 over 6 then is 1/2. 4 over 6, right? So 4 over 6 here is 2/3. So this is 2 pi over 3, right? 4 6 and 2/3. So 3 6, 4 6, this is 5 6, that doesn't reduce. This is 5 pi over 6. Then 6 6, which reduces. Then 7 6, which doesn't reduce. 7 pi over 6. Then 8 pi over 6, 8 6 does reduce, that's 4/3. So this is 4 pi over 3. So it's 8 6, 9 6, which reduces. 10 6, which does reduce. 10 6 is 5/3. So this is 5 pi over 3. With that 10 6, 11 6 does not reduce. So 11 pi over 6 there. And then, so 11 6, then 12 6 does reduce to 2. So that one works out nicely. Okay? And that gives us all of our angles then. really, if you do that pattern with the pi over 6s and the pi over 4s, you'll have everything you need, okay? You wouldn't have to do that necessarily with any of the other angles, but it will work. If you want to do this with 60s, you go 60 is 1/3, this is 2/3, 3/3, 4/3, 5/3, 6/3. Okay, so you can get that to work out with all those angles. Okay, so now that I have the angle measure, or the arc length in this case with the unit circle, then I can get my coordinates for each point. So the coordinates are simply translating these over and again adjusting the sign appropriately. So 1/2 comma √3/2, if you move it over to the second quadrant, the x value changes sign, the y value stays because you're moving to a negative on the x but staying positive in the y. So this would become the point -1/2 comma √3/2. Then the 45, which is really 135, you take the √2/2, bring it over and change the sign on the x. So it's -√2/2 comma √2/2. Then we take the other point there, √3/2, change it to a negative, and then keep the 1/2. Okay? So all the x's change sign, the y's stay the same. Okay, and again, they're all the same height, that's why the y's stay the same, just the x values are reflected over. Going down into the fourth quadrant, you change both signs. Okay, well, not change, you make both of them negative. Okay, so here, the 7 pi over 6 relates to the 30-degree angle, or in this case, the 150. And so you end up with -√3/2 comma -1/2, both are negative. Then down here you would have -√2/2 comma -√2/2, and I'm going to do this a little bit faster. We're going to end up with -1/2 comma -√3/2. And then we move everything over to the fourth quadrant, and in the fourth quadrant it's the y's that are negative, but the x's are positive going to the right. And I should do the axes as well, but you guys probably know those. It's -1 comma 0 for the x, and 0 comma -1 for the y. And then going up the side here, again, the y's will be negative, but the x's will be positive. So it's going to be 1/2 comma -√3/2. This one is √2/2 comma -√2/2. And then here is going to be √3/2 comma -1/2. Okay, so that fills in our entire unit circle. This is useful again in finding trig values. So now I can find trig values pretty quickly, or trig function values. Let's say I wanted to look at the sine of 7 pi over 6. Well, I know the sine is the y value at that angle. The y value at 7 pi over 6 is -1/2. Okay, so I can pretty quickly, once I know this, or have established this unit circle, I can pull off those trig values pretty quickly. If I wanted, for instance, to find the cosine of 3 pi over 2, well, the cosine is the x value, angle 3 pi over 2, x value is -1. Okay, or if I wanted to do the tangent of 7 pi over 4, well, that's simply the tangent, the ratio of the y over x, and of course that ratio is -√2/2 over √2/2. Well, those are kind of nice because if you have the same thing over itself, it's 1. One of them has a negative, so it's just -1. Okay, so the tangent of 7 pi over 4 is just -1. Okay, so we can pretty quickly find those values now. I do want to look at some limitations now on the trig functions. And so I mentioned in the previous video that the farthest the x values go are 1 and -1, right? All the other x values and all the other points are somewhere in between. If you just focus on the x axis here, all the points in the circle are between -1 and 1. And all the points in the y direction are between -1 and 1 as well, right? So the point over here at 7 pi over 4 is somewhere between -1 and 1 in the x direction and somewhere between -1 and 1 in the y direction. All of the points are. And so all values of x and y are between -1 and 1, okay? And we know that the radius is 1, right? And r equals 1. I'm gonna rewrite those. There we go, I like that better. Okay? So all values of x and y are between -1 and 1, and r is equal to 1. So that puts some restrictions on the values of the sine, cosine, tangent, and the cosecant, secant, and cotangent. Namely, because the sine is equal to the y value of each point, we know then that the y values are between -1 and 1, so that must mean all of the sine values are between -1 and 1 also, including the endpoints. Alright, so we can say that -1 is less than or equal to the sine of any arc length or angle, which is less than or equal to 1. So the output from the sine is always between -1 and 1, okay? The same can be said for the cosine, because the cosine is actually equal to the x value, right? And so with a similar argument, I can get the cosine to also be between -1 and 1, okay? So -1 is less than or equal to cosine, which is less than or equal to 1. It's in that interval. The outputs, these are the outputs, remember. But the inputs can be anything, okay? So I've just gone around the circle one time, right? Gone around the circle one time. But remember that you can get coterminal angles when you go around the circle multiple times, right? So I could get, if this is 1 pi over 2, 3, or 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2 gives me back up to a 90-degree angle. 5 pi, 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, 10 pi over 2, you know, and then you just reduce those fractions. So you can get angles that keep going out infinitely large, or you can go negative by doing them clockwise, right? So you can go -1 pi over 2, -2 pi over 2, I'm gonna twist my arm, -3 pi over 2, -4 pi over 2, -5 pi over 2, and so forth. And you can wind this around clockwise or in a negative direction. And it doesn't have to be the pi over 2s. You can do that with any of these fractions going around. I'm just using pi over 2 because it's just quicker, nicer to do it that way. So the domains, remember, you may not remember this, you may remember this from an algebra class where we talk about functions. But these are trig functions. You input a value of an angle, get out a value of a ratio, or in this case an x or y. The domain of the sine and the domain of the cosine are just all the angles that give you outputs. And it could be anything, right? It could be big positive numbers, big negative numbers, doesn't matter how big, how small. And so the domains of these, the inputs, could be anything, all right? So domains of sine and cosine of s, domains again being the inputs, are going to be negative infinity to infinity. It's anything, right? All real numbers. You can plug anything into any angle or any arc length into the sine and cosine, and you can get a value out, okay? Let's look at tangent for a moment. The tangent, well, the tangent, remember, is the ratio of the y over the x. Interestingly, that ratio can be pretty much anything. If you have 0 over 1, we saw that that was equal to 0. If we have, we could go up to 1 here. So 1/2 is smaller than root 3 over 2, so the y over the x value there is less than 1. Here it's equal to 1. Here it's greater than 1. Here it's undefined. And so you actually end up with all numbers being outputs for the tangent, okay? All possible numbers. So any point in here, if you take the ratio of the y to the x, you'll be able to find some number between negative infinity and infinity. In fact, there's even some values here at pi over 2 and at 3 pi over 2 where the tangent is undefined. So those are some values we can't use, okay? So the tangent, oops, I don't want to write that. The domain of tangent s, oh, not the domain. I want the output. I'm talking about the outputs, right? So the outputs are the range. I'm sorry. These are the ranges here for the sine and cosine. So the range, or the outputs, for tan s is all real numbers, okay? It's all those ratios. The domain is the problem. Domain's what's the problem here, because in the domain you cannot include pi over 2, because that gives you an undefined tangent. You cannot include negative pi over 2 or 3 pi over 2, either one. It's the same thing, because it has an undefined tangent. And so the domain for tangent of s is all real numbers except your odd multiples of pi over 2, right? 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so forth, if you keep going around. Or negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2. So it's all the odd multiples of pi over 2. You could actually express that algebraically. If you want to find odd numbers, you just take an even number, which is 2 times a number. Any even number can be represented by 2 times a number plus 1, right? 2 times a number plus 1 will always give you an odd. And if you take that and multiply it by pi over 2, you'll get an odd multiple of pi over 2. That'd be like your 1 pi over 2, 3 pi over 2, 4 pi over 2, and so forth. Of course, in this representation, that value I put in, or that variable I put in for k, has to be an integer, like plus minus 1, plus minus 2, plus minus 3, and so forth. Okay, so those are just some quick properties or restrictions on the values of the outputs and the values of the inputs for the trig functions based upon this unit circle idea. What's also interesting, I mentioned that the sine and the cosine are always between always between negative 1 and 1. Then that also means their reciprocals, which are the secant and cosecant, will always be greater than 1 or less than negative 1. So if you think about it for a moment, if you were to take a number between 0 and 1 and do its reciprocal, right, a number between 0 and 1 has a bigger number on the bottom than on the top of a fraction. If you flip it, the bigger number goes on the top, and so what you get is a number that's bigger than 1. And if you take a number between 0 and negative 1 and flip it, you get a number out here less than negative 1. And so what you end up with is the output outputs for secant and cosecant are either let's see, you had 1 to infinity, so everything greater than 1 or equal to 1. Either that or they're going to be in this interval from negative infinity to negative 1, including the negative 1. Okay, so it's either going to be everything beyond 1 or everything beyond negative 1. Okay? And so you're never ever going to get a secant value or a cosecant value that's between negative 1 and 1. It can't happen. So if you ever find that the, let me give myself a little space here. If you're ever asked to find a secant, or find S such that the secant of S is, or secant of S is equal to like 0.5, right, or 1/2. Well, there is no value because the secant can never be between negative 1 and 1. It's always going to be either bigger than 1 or less than negative 1. So there would be no solution there. Okay, because there aren't any angles or arc lengths that would give you that output for a secant. All right. Okay, good. I think that pretty much does it for our discussion on the unit circle. There's a lot in this section. It's a pretty heavy section, but I think it gives you some ideas, really gets you to practice playing with the angles and with the outputs and inputs from a trig function, and of course remembering your positive, negative signs in each quadrant and all that stuff. So lots of good practice here in this section.